Hello, and welcome back to Neural Networks from Scratch in C++. In the last video, we were talking a little bit about inference versus training. And recall that inference has different assumptions than training does. So remember, I know that this looks a bit complex. Don't worry, we'll break it down. But what you did see before in a previous video, we definitely saw our inputs on the left and we had our outputs on the right. And we're trying to build a digit classifier. So a classifier that, well, classifies digits between 0 and 9 inclusive. So recall that in inference, we were talking about these outputs, and we were questioning, okay, how do we know that these outputs actually represent the digits that we say they do? Well, we were talking about how training is the process for us to actually be able to say that these represent digits by essentially having some desired behavior and moving towards exhibiting that desired behavior optimally. And inference, we're not updating the weights or the parameters at all. We are just taking what was given to us by training, and we assume that these now represent digits. So those are the different assumptions that we have for inference and training. So I really want us to get to the inference part, so actually coding out a neural network that classifies digits. And we're going to be doing that in the next video. So I'm going to be providing you with already trained parameters. So we're going to now, in the next video, we'll be in the mindset that, okay, we have something that actually spits out digits. We just need to code up the neural network. So it allows you to, you're relieved of a lot of different assumptions and theory that you need to know, since we're just going to be focusing on inference there. But before we get there, I need to introduce a little bit more vocabulary. And it's not a lot, but it's very, very important. And there are a few important terms and one important theorem that I'm not going to prove, but I'm going to just lay out as a fact that you just need to know, and it's going to motivate a lot of the complexity that I drew out here. So yeah, it looks complex, but without this complexity, we would not be able to have neural networks that actually perform well. So let me try to explain, motivate some of these areas that look like very, very complex. So I'm going to introduce some new vocabulary, and we're going to be starting with the concept of layers. So there are three different types of layers that we have in neural networks. And the layers, essentially, they're matrix multiplications followed by something else that I'll get into in a bit. So we have these three different layers: input layers, hidden layers, and output layers. Input and output are a little bit more self-explanatory. Hidden is a bit more complex. Okay, so what is an input layer? Well, an input layer is a matrix multiply followed by something else, which I'll get into, that takes in your interpretable input features. So this is data from your data set, and that is the input to this layer. Whereas the output layer takes in some features, does some matrix multiplication, and produces output features. So during inference, we can assume that these actually represent the outputs. So that's why it's pretty self-explanatory that we call this the output layer. And then the hidden layer, as I said, it's a bit more complex. But before I get there, I want to talk about that something else that I brought up after every single layer. So I said you do a matrix multiply followed by something else. And that something else is called an activation function. So an activation function is an element-wise operation that you do on every single output after the matrix multiply. And it's an element-wise nonlinear operation. So I've drawn two examples of nonlinear functions, but you could have a bunch of different nonlinear functions that you could apply. So this is something called the sigmoid function. This is called a ReLU function, and you might think it's linear, but it's only linear from 0 to infinity. Whereas over here, there's a nonlinearity point for at 0 and for like all the negative values. So because we have this kind of bent shape, it's definitely not linear. But we could have a bunch of different nonlinear functions. They're arbitrary. I just showed a few examples. So for every layer, you do a matrix multiply followed by an activation function. So here's an example of, let's say that our output of a matrix multiply produced this vector, and we put it through the x squared function. So then you element-wise apply x squared to every single input. So 7 squared is 49, 5 squared 25, then 4, 1, and then 9. So why do we need these activation functions? And what are these hidden layers like? This just sounds so mysterious, and what's hidden about them? Okay, so let's talk about the hidden part first, because that's easier to explain. So the reason why the input and output layers are called input and output layers is because the input takes in, well, we know exactly what it takes in. It takes in inputs from our data set, and our output layer produces our outputs, which are our digits. But if you were to do, say, this matrix multiplication followed by an activation function, well, like what does this, for example, what does this vector here actually represent? And then you do another matrix multiply, and you get some other vector, you do an activation function, and okay, you're left with another vector, and you do that a few times, and then finally you get to your output. Well, what did you have? What were these features in the middle of the network? Like, what did they actually represent? And that's the tough part. Like, there are ways now to use analysis to maybe understand what's going on in the middle, but it's not a given. You need to do some work to be able to potentially understand what these are. But the reason why we need these hidden layers is due to a theorem, a mathematical theorem, which I'm going to just lay out and not prove. You just take it as a fact unless you want to do some further research. But the idea is that if you have a neural network, if you have at least one hidden nonlinear layer, so that's a hidden layer with an activation function that's not linear. So pick any activation function other than all of like the possible lines that you could get, right? So don't choose these, choose one of these. So if you have a neural network with at least one hidden nonlinear layer, this can approximate any function on a finite interval. So for example, let's say I wanted to approximate the sine function between, cosine function. In this case, it's cosine. It could be sine, any shifted sinusoid between some interval a and b. Essentially, what it's saying is that if I have at least one hidden layer with a nonlinearity in the middle, that if I choose the right weights and biases, I can output this function. And you can pick any function. It could be a parabola, but these are all like scalar valued functions. But you could also have multidimensional functions, like the case for our digit classifier. Instead of just producing one output, we're producing 10 different outputs. So what the universality theorem states is that if we have at least one hidden layer with a nonlinearity, let's say that there exists some function that classifies these digits the best. What this says is that you can pick parameters in this network that can approximate that particular function to any degree of precision on a finite interval. Okay, so that is why we need these hidden layers, and that is why we need these non-linear activation functions. If our function we were trying to predict was linear, we don't need these, but most functions, most interesting functions, are not linear. And what's interesting is that by just giving the network a desired behavior and moving the parameters to maximize that desired behavior, what this says is that at least by having one hidden layer with a nonlinearity, we have the chance of stumbling upon parameters that approximate that function with arbitrary precision. So training does not give us guarantees that we're going to find the optimal function. All it's saying is that every step that you make is going to potentially be better than where you were before. And that's confusing, but don't worry. When we get to the training videos, it'll become a lot clearer. So let's just do a bit of a recap. We introduced the concept of the input layer, the output layer, and the hidden layer. And in principle, like they're the same thing. It's just matrix multiplication followed by these pointwise nonlinearities. But the main, I guess, semantic difference between them is that in the universality theorem, it specifically states that you need at least one hidden layer that has nonlinearity. And this, if you choose the right parameters, you can approximate any function to any degree of precision. Okay, so now in the next video, we're going to actually classify digits, and I'm going to provide you with a set of parameters and activation functions that are going to well classify a bunch of different input digits. Once we go through the process of actually writing down the neural network in code, you'll have a lot better intuition for what's going on, because training, there's a lot more theory that we need to get into to discuss how do we actually how do we move the parameters in such a way to find the optimal function that classifies digits. Okay, so there was a lot there, and I'm sure it might be helpful to rewatch this video, maybe once or twice, take a lot of notes, but don't be worried if you don't fully understand even then, because I feel like once you get to the code, and once we just kind of go through the process of writing it out, it's going to make a lot more sense. So I hope to see you in the next video.